of today, I wanted to get back to this issue of programming style. Talking about clean code that's easy to understand, easier to appreciate, etc. And you know, last time I sort of made some general points about characteristics of a good style. It should be straightforward. It should be natural. You should use meaningful names. It should be neatly formatted, consistently indented, for example, have helpful comments, and consistent. And we talked about some bad smells, some things in code that we look for that are worrisome. They indicate vulnerabilities. They indicate dangers. That if we don't remedy them, it's just dressing for booze. It's just asking for trouble. Someone's going to make a mistake with this code with 25 likelihood, and that can yield bugs, and that can yield hours of debugging, which could otherwise be easily avoided. So long duplicate code, long routines, cases where there's too many parameters, where you're using global variables willy-nilly across your code, and a variety of other things which relate to your learning in 270. Deep ifs, deep while loops, etc. And on your first problem set, ladies and gentlemen, your first assignment to be handed out next week, there's going to be a large exercise involving this. Okay? So those bad smells, which I'm just flashing up here, will be useful to refer back to when you're thinking about what could I fix about it. And we talked about using defensive programming. We're going to later talk some about offensive programming, which is not about being obnoxious or arrogant. It's about proactively trying to get the program to reveal faults that otherwise would have been hidden. Here we're going to be talking about defensive programming a little bit, and some of the aspects are things that deal with those bad smells. So use comments throughout, use good naming conventions, pay attention to formatting, separate commands and queries, avoiding manifest constants, avoiding just numbers that appear in your code without a name associated with them. These things are all dangerous, and we're going to be walking through some examples today and next time which sort of illustrate these sort of things. And I have a bunch of other suggestions here we don't have time to go into. What I really wanted to talk about today was finish up a little bit of discussion from last time on naming, and then go on to a bunch of examples where you see some of these principles in action. You get to see in concrete terms how you can clean up a bit of code. Okay? So last time we had talked about naming. We had talked about using names in a conscious way to lessen our risk, to document, to be clear, transparent to others. So, you know, within C, for example, we talked about C++ classes are almost invariably uppercase. Sometimes they start with the letter C, uppercase. But, you know, functions, for example, in C, or methods and fields in C++, if it's a thing that returns conceptually Boolean, you have a name is this or has that, something that in English suggests this is true or this is false. We denote methods which do something, which accomplish something, which change something, but running them twice will not yield the same result often. They don't just compute a value, they actually modify something. You name it with some sort of action. Process this, or write this to this, or you know, save this, etc. But then there's a lot of things which are functions which just compute values. So you could use get, or you could use, you know, calculate this or compute that, and things which convert between different sorts of values. Okay? Constants we traditionally put in C in all uppercase. So if you account define, that should be used in of a constant. It should be all uppercase, and use an underbar to separate it, because you can't use so-called camel case, where we alternate uppercase letters and lowercase to separate words. And generally, sort of the smaller the scope or the span of a variable, the shorter the name is often used. But generally, you'd want to keep them keep them clear. Now, there's a bunch of information we can encode in the name, and that I'll expect you to think about including. What type of thing is it referring to? Or we talk about the max one, the min one, the count of them. Sometimes a unit or dimension, like miles per gallon or what have you. What sort of information is it? Is it a method? Is it a pointer to a function or what have you, etc. We talked about values of this. So I want to highlight something that you'll see in a lot of languages, which is use of singles. How many people here have done Perl programming? Okay. And you'll see a similar use within certain shell scripts. Actually putting symbols before a name or after a name to indicate the sort of quantity it is. So how many people have done basic before? Okay, a somewhat large number. You may remember a dollar sign or something like that to encode a code called string. So to say you encode a name, you would use a dollar sign. The dollar sign means, hey, this is so it's a sequence of characters. In Perl, you have something like $i to indicate a variable that has a number of values associated with it, or arrays indicate with an @ sign. These are built into the language, the conventions here. In other times, like in Microsoft documentation, you will routinely see the use of this so-called Hungarian, which I kind of mentioned in passing last time. So there, Booleans are indicated with Fs, strings that are terminated with, as is traditional in C, with 0, a null character following it, are labeled with SC. A thing that's used as an index is labeled with a lowercase I. So this is, for example, the number of the payee maybe in some array or some database is person 0, person 1, person 2. Arrays are labeled with RG, indicating it's a range, and P indicates a pointer. So if you look at Microsoft documentation on their API, you will see these types of things used quite a lot in C-related code for Microsoft. Okay, so the simple Windows API, etc. And there's actually different dialects of these things. So just be aware that in certain sub-communities, you're going to see heavy use, subscription to certain conventions, and you should be aware that they're systematic in many cases. Okay. Now these things are really, really useful if we want to keep track visually of what's going on. An example is this whole issue of safe and unsafe strings. That sounds bizarre. What can be an unsafe string? You know, is he going to attack you or something? Well, folks, you can tell me. I talked about security before, and some areas where security is most important. Where could we be dealing with a situation where something we get from the user, I'm going to give that away, could be dangerous? Sorry? Okay, a credit card number? Okay, a password? Okay, that sort of information might be private, but credit card number is an interesting case. From where would it originate that we'd have to be especially concerned about being dangerous? Ladies and gentlemen, anytime you get something from the user through a user interface that's publicly available, say through the web. So if you're building an online system of some sort and you have fields, like maybe it's a search field, like Amazon has, right? You have Amazon, you go there and you can search for something, or YouTube or what have you. If you're building sites like that, you've got to be almost paranoid that people are going to try to break in, because they will. Within a 6 months time on a server, there's no information of value here. I think they're going to make 5 break-ins in 6 months. And it's just incredible. It's a nasty world out there, and people will try to break in. And one of the key ways they can break in is by putting things that are devious into fields on your web pages. And specifically, they put in programming language code that can be executed. Now, you may be surprised at that. I mean, after all, who would sit there entering C statements into Amazon? Well, you don't put in C. What you put in is a language that's used for databases. Okay? Why do you do that? Well, because if the people who built that site were sloppy, or to put it another way, if they weren't really, really pasting in whatever's in there into a string to give to that database. So you know, they'll say select, you know, whatever was, you know, select, you know, foo, some field foo. Maybe it's select, you know, customer name, or customer surname from some table. So from customers, where you know, ID equals, and this is whatever you typed into the interface. Or it'll say, you know, select it from books where the title equals this. And if they're not careful, this information could in fact be a string just like this, which basically says, give me the list of all credit card numbers on this site. And it actually will pull back information and print out information to that user if it's been sloppily done, which would show all the credit card information to the site. They actually give programming language code into the interface so that it will be pasted in here and reveal information to them. So we have this notion of safe strings and unsafe strings. Safe strings are strings that have been checked. Unsafe strings are strings that could have originated with the user, and we're not sure yet if they are legit. We're not sure yet if they've been sanitized in a way that would strip out danger. And so you've got to kind of maintain that some variables there's these unsafe strings and some there are these safe strings. By naming them appropriately, you can distinguish them. And you'll never mix one with the other. They always, before you becomes a safe string, it will have to go through some process of cleaning it up, of checking it, make sure it's safe, and all those sort of things. Another thing is distinguishing common characters from common bytes. Ladies and gentlemen, when I was your age or a little bit younger, the world was a simpler place when we built software. Because typically we were building it for English language customers, or English and French and Spanish European customers, European language customers. And what that meant is that we could use a single byte to encode a character. That's no longer the case. Turns out to encode Chinese characters, you need several bytes. Turns out to encode many non-European-based languages, you'll need several bytes. You need so-called Unicode encoded things. And so now we have to distinguish between number of bytes versus number of characters. A given string of 3 characters might take, you know, 12 bytes to encode. And so if we have a count around, we could say that this is a count of bytes, this other one is a count of characters, and we don't confuse the two. I talked last time about a problem confusing different types of units, and you know the list goes on and on about how you can protect yourselves. So you know often you're going to want in your code to use it to capture what is the sort of thing I'm dealing with. For example, is this an income? And if so, maybe it's the maximum income. So you have a variable called income max or income min, or maybe it's the mean of the income, the average over some population, or total across the population. So, you know, encoding that in the variable name will often tell you something about where it came from, how it can be used, etc. What sort of value it is. We talked about Booleans and so on. In certain languages, you use question marks. So in Scheme, for example, and other Lisp languages, you can use a question mark to say, for example, you know, question mark open. So one of the most frustrating things in C coding is that a lot of things can start to look alike because functions are often named with all lowercase letters. And you're looking at code maybe late at night, and you think you see one thing, but actually what's actually there is different. So an example is this thing up to the right. Anyone notice anything odd about that in the upper right? Yeah, it takes a long time. What's off about the thing in the upper right? Exactly. But believe me, if it's midnight got to get something into your box the next day. For your customers, you've got to roll out a new website. You're trying to fix a bug, which is causing people from China to be unable to access your website. It's easy to miss something like this. It's easy to kind of miss things that are quite similar, and you're expecting to see one thing, and you impose that on what you're actually seeing. So you actually twist what you're seeing to kind of fit your best guesses as to what should be there. So, for example, in C, we get these problems like this. Maybe you have a variable called, stoppt, and maybe it's a function name, and what you really meant is stcppt. And you look at that, and it doesn't strike you that actually that's an O instead of a C. Shift RN, Shift RN. It's very, very easy to just kind of overlook the fact that the difference. It seems obvious, perhaps, from your distance up here, but it's not. When you look at it, you are assuming it's one thing and it's actually another. So the goal here is to try to use names that don't look too similar. Actually, name consciously so that things look distinct. So product versus sum, for example, would be a something which is fairly distinctive. Okay, so those are some principles here. I'd like to go through some examples here. So we're going to talk about a set of examples, and I'm going to be providing some of these in some slides. This name should have been updated there, but I'm going to be providing some examples that you could download from the Google site probably in the next day or so that will illustrate some of these things. So here's one expression in C. What is this expression trying to do? What is it testing? So it's using this block heading, and assume that these things over here are some limits or constants against which it's comparing. So they're variables that encode the limit or constants that encode the limit. What is this actually testing? So that's sort of a transliteration of what it says in English, and that's absolutely correct. And in short, what it's really testing, I could tell you, so if I can unpack that in a shorter form, it's testing does block ID lie between ACT blocks on the one hand, inclusive, and UN blocks on the other, where UN blocks should be greater than. In other words, does it lie within this range of ACT blocks up to just one before UN blocks? So in short, you could actually simplify this considerably if you say something like this. It's kind of what we call an idiom. It's just somewhat easy to understand. We don't have to kind of twist our head around these knots or here. What this is saying is that, okay, block ID is greater than this thing, and it's greater than or equal to ACT blocks, and it's less than that. In other words, is it in this range from ACT blocks to UN blocks? I would argue that actually an even cleaner way to do this, might be to have a function. If you're doing this a lot in your code, you could have a function called, is in range, and give it block ID, and give this as the lower range, that is the upper range. And it would take care of this, and you would just say if is in range block ID, comma ACT blocks, comma unblock, UN blocks, and it would figure out, okay, is it in that range, and you wouldn't have to look at this expression. How many people here feel this expression is clearer than this one? Okay, yeah, if it's not universal, it's at least pretty compelling to a lot of people that there's an improvement here. This is an example of simplification that we're going to be, that you're going to see throughout your life if you write code. There's going to be lots of opportunities for this. Okay, here's another issue. I think folks have worked with C for a while. taking the representation of x, and maybe x is a short integer here, and so it's got maybe it's even a single byte, for example, just to simplify things. So maybe it's got some bits in it and something like that. So here's the first nibble, the second nibble, and we want to then AND it with some so-called mask. Maybe the mask is this, and it will extract therefore this component. So it'll be 0, 1, 1, 0, and then all zeros after. So it's a so-called bitwise AND. It has to be both. It has to be 1 in here and in here to be 1 here. Otherwise it's 0. Does that make sense to people? Okay, but what is this actually? So what job is this expression doing? What is it telling it to do? What's bothering you? What's preventing you from answering right away? What's one interpretation of this? I'm not saying it's the correct one, but what's one interpretation? Okay.
Compares mask to bits and then hands that.
Okay. Okay, so that's one possibility. Maybe it's doing this first. It's first computing is mask equal to bits. In other words, this guy here. And then it's taking the AND with x. What's another interpretation? Yeah, maybe it's first computing x and mask, and then it's comparing to bits. Now this is troubling, because especially if you don't realize that it's ambiguous. You just glance at it and think, oh, immediately, well, it's obviously taking x and the mask. But it depends. What does it depend on? How this is interpreted, what does that depend on? Yeah, it depends on the order, the so-called precedence of operations. See, that's what we call it. Precedence. So P-R-E-C-E, precedence. P-R-E-C-E-D-E-N-C-E, okay? It depends on what's the precedence of equals versus and. Now, one could conjecture what that is, but one could enforce it. If you want to be safe about this, you want it to be obvious to someone so that they don't have to walk around with a C manual in their hand or in their head, you could make it clear by parenthesizing it. Now, there's an unhealthy subculture of a minority out there that actually takes delight in being C wizards, and I don't know if to put this in, but it's foolhardy. It's reckless, it's foolhardy. This is just much, much clearer to someone. Even if that original thing were interpreted this way, it's much, much clearer if you consciously put this in parentheses, because it makes clear what you are trying to do, and it makes sure that someone won't misunderstand it, someone who may be new to C. Someone, ladies and gentlemen, perhaps even like you. So here, putting parentheses around things makes it clear. Okay, so here's another example. So what is this thing doing? What is this EOF thing? End of file. So this is doing what? What could this be doing? Okay, and it keeps on doing that until the. Okay, so that might be the intention here. So we're reading each successive character, say from this file. Maybe it's stood in, right? By default, if we haven't gotten it open something up, and it's reading each decimal until it gets the end, until I press Control D, which by the way is EOF. So I press it in Linux, Control D, and then it finishes up. So it's going and execute whatever it finishes with. Now, what's a possible ambiguity here, though? Again, along the same lines.
It could be assigning C the value of the comparison.
Yeah, exactly. Maybe it's actually, maybe by default we think it's computing this, but maybe it's actually first, this first, C equals get char, and then comparing if it's if it's not equal to EOF, the value of that. But maybe first it's doing, computed get char not equal to EOF, and then assigning that to C. So again, that's not so clear. But if we do this, it becomes much clearer. And in fact, there's a this is incorrect. So excuse me. Let me get this should be corrected. That's what was meant. So this is going to be much clearer. Okay, first we're reading this character, we're assigning it to C, and then we're seeing if that's not equal to EOF. So we're eliminating this potential ambiguity that someone might reasonably have as to what's going on. Because if we don't, even if we're correct that it works, a person may be mistaken, they may be thrown off by it, that it'll take extra time and extra burden on them to think, is this correct? Imagine you're debugging this code, you might say, is that really correct? It just wastes your time. I mean, just you could put in these checks, it just makes it very, very clear to someone. Okay, so here's another symbol. How could I improve this code? You could tell me. You recognize this, you should see certain patterns. What could I do to improve this code? To eliminate the ambiguity. Okay, parenthesis. What could I parenthesis here? Truthfully. Where should I put the parenthesis? Okay, around each comparison. Okay, so I could do that. Will that systematically eliminate all the potential ambiguities? Okay, what other parentheses could I put in? Yeah, each of the modulus operators, because after all, someone might reasonably not remember, does this have a higher, does an equals or not equals have a higher precedence than modulus? In other words, is this going to first compare 4 to 0 and then take that modulo, the results of that? So we could put this in, but we might reasonably put in parentheses around each of these as well, more completely. Okay. So this is another thing which I see a lot in student code. These complex expressions. Maybe I will stop this now, just so